Welcome and a very good day. So today we are going to cover chapter 4.5 on recycle, 4.7F on product separation, bypass and purge. For a reactive system, we have to reconsider the conversion, right? The conversion of the reactor has to be taken into account prior to setting up the boundary analysis and perform the material balance calculations. There are two definitions of conversion for a reactive system that you had learned. The first one is a single pass conversion. The single pass conversion is just the amount of reactant that is going into the reactor minus the amount of reactant going out of the reactor divided by the reactant input. All of the unit of this reactant are in mole or mole per minute, right? So the unit for single pass conversion is dimensionless. It has no unit because it is just mole over mole, so they can cancel each other. So the boundary analysis for a single pass conversion will be around the reactor only. So you can see that you have the XR and you have the YR. So you are looking into how much the raw material is actually converted to a product. So we will examine the amount of materials that's going in and out of the reactor and set up the material balance equations around the reactor. So the conversion data, okay, this conversion data that you get there will be the extra information added in the degree of freedom analysis. The overall conversion is defined as a reactant input minus reactant output from the process divided by the reactant input. Okay, you can see from the diagram that it covers the overall system that are included in the process. Still, the units are for the reactants are mole or mole per minute. And you can see that the reactant input from the first unit minus the reactant output that comes out in the final unit divided by the reactant input of the first unit, right? It's not around the reactor alone. It is for the whole process. Means that if you are looking into the boundary analysis, the boundary is the boundary for the overall system. Also, please read the process description carefully. Look at what compound is being converted or conversion that was presented in the process description refer to which product. Okay, the diagram that I give here is just an illustration of a process with a reactor and how we perform a boundary analysis to show the overall conversion of a reaction. Okay, let's now set up the boundary analysis for multiple unit processes with recycle stream and a reactor. For this process, we have two units operations, which are the reactor and a unit that I call as B, but this is basically a separation unit, all right? So unit A is a reactor and unit B is a separation unit. Using the concepts that we have learned, we are able to set up 4 subsystems for this unit. Okay, so what we have here is the first boundary is the boundary that covers the overall unit in the process. Okay, and for this particular boundary here, which I will label as A, because there is a reactor that is involved, then you can do an atomic balance to set up the material balance equation. Okay, so the stream of interest for this overall unit will be stream 1 and stream 3. Okay, the second boundary analysis is around the reactor. because there is a single pass conversion information given, then you can do the atomic balance, okay, to set up the mass balance equations for inlet stream 1A and 2. Okay, so you will have 1A is equals to 2, and you are going to use the atomic balance to do that. The third boundary that we can set up is around the mixing point, as I shown here. Okay, I shown it in circle. So that mixing point connects stream number 1A, and stream number 4. Because there is no reaction in this stream, then you can do a molecular balance, right? Because it is a non-reactive system, so you can perform a molecular balance to solve for the material balance equations. The same goes with our boundary number 4, which cover unit B, because unit B is also a physical unit, so we can perform a molecular balance to solve or to set up the mass balance equations. So you can do a proper mass balance equations that relate stream number 2 is equals to stream number 3 plus stream number 4. Just a questions to ponder. Okay, if you have a single pass conversion of 60%, what will be the overall conversion if the separation is complete? Okay, and all your feed material is recycled back to your feed stream. So just relook at which of the 4 boundary that you had developed will cater for these questions. All right, what are the implications of having or not having a recycle stream in our process? If we are looking at the reactor conversions around the reactor, or what we know as a single pass conversion, then our reactor or the reactor that we design should have high yield. High yield reactor usually is very costly, and for maintenance, it is also very high. But the good thing if we have a high performance reactor is that we don't need a extra separation process, and thus we can reduce our recovery cost. But this is of course not a very practical step in for our process industries. But when we look then into another system where we have to consider the overall conversion, then we will have a much more practical approach where we will have a reactor that have low yield, high throughput, much cheaper to maintain, much cheaper to buy, but we need to have extra unit to recover and recycle our raw material. So when we have this, then we have to think again whether recycle is practical or not for our process industries.